And welcome back. In our final video in this module, let's actually talk about other floating point representations. We like the single precision 32-bit representation, but are there others out there? Yes. What if you need more? What if I need more precision to get more accuracy, hopefully? Well, let's just double it. I've got 64 bits. Many machines now are 64-bit wide architectures. Let's actually think about having a 64-bit floating point number. By the way, this works on 32-bit machines. So it just one by one sends the top 32 and the second 32. So it'll work in smaller machines. This could work on a 16-bit machine. It could work on a 1-bit machine. Just send all 64 bits one by one. So it can work. We call this binary 64. The other one we called FP32 or also binary 32. This we call binary 64. This is the next multiple of the word size. And so now look at the size of this. 11 bits of exponent. 52 bits of significand, called a double. You've seen floats and doubles. By the way, doubles are great. And so I encourage you, if you ever use any computational science, anything where you need a floating point value, use doubles. If you use small ones, you're doing some change and fraction stuff, floats are fine. But if you're actually doing some calculation where you need big numbers or small numbers and much more accuracy, you're going to use a double because that precision can buy you that accuracy. How big and small can you get to? Well, 2 times 10 to the minus 308 is pretty small, times 2 to the, all the way up to 2 to the 10 to the 2 times 10 to the 308. So that's pretty big. Those are big numbers. And again, that significand is really the key here. Are there bigger than that? Yes, there are. One is called quad precision, 128 bits, otherwise known as binary 128. Again, unbelievable range and precision. 15 exponent bits and 112 significand bits. Do we have oct precision for people who need even more? Yes, that's called binary 256. What if you actually need less? Does binary 16 exist? Yes, it does. That's half precision. That's using what was known as short or 2 bytes to store that, and that's 1, 5 exponent, and 10 significand. There's another comparison called B-float 16, and B stands for brain. And the idea is, what if you kept the exponent width the same? Okay, let's take a look here. So this is my 32 bits. There's my 1, there's my 8, there's my 23 for FP32. If I said, I only have 2 bytes, not 4 bytes to store a float, then, well, let's kind of keep the same ratio. I've got a 1, a 5, and a 10 in here. But what if you wanted to keep the same big to small range? Well, wouldn't it be nice if I kept the same 8? So actually, notice this width is exactly the same. B-float 16 stands for brain floating point format. And this is the same 8. Notice it's the same 8. I just sacrificed precision, okay? So this is a lot smaller. This is 1 out of 16. It's 1, 8, and 7 has to be, obviously, right? So that is a little smaller, and that's used for faster machine learning. And in fact, there's now an entire soup of people interested in doing machine learning, deep neural nets. There's now a TF32, which also has 8, but has 10 significand bits, and it's 18 bits. So it's not a multiple of 8. That's a little weird. And in fact, domain accelerators have even more support, or okay, I would say a spotty support of all of them all. I'm looking at this table, and the key thing I'm seeing is this NVIDIA is the only one who supports all of them. Notice that most of them support different sizes. Like, well, to optimize, I'll only work with the B floats, or I'll only work with int 8s. And by the way, there's int 4 as well. This means an integer. By the way, this means a nibble. This means a byte, right? This means 2 bytes of that. And then the floating point space, these are not all supported by all of these domain accelerators. So think about that when you choose the particular domain accelerator that you might pay for on the cloud or try to buy yourself or build yourself. So those are not full support for all the different kinds of numbers that we're going to use. Here's a really interesting idea. This is Dr. John Gustafson. He said, remember what we didn't like about fixed point? You kind of locked in where the binary point was. Let's be clever. Let's have 2 numbers in which you saw that all those previous formats locked in what the sign bit was, the exponent bit was, and the significand bit was. You saw them, right? All the different things. So he stepped back and said, well, why don't we abstract it even more? Why don't we allow you to be able to vary the bit width of the exponent and significand. You see that connection? And so that's his idea. So what if you made that variable? So it's almost like a third variable. This tells you how many bits for an each, or maybe just where that line is. And then these two is what the exponent and significand are. He's also going to add this very clever idea called a U-bit that says, you know, remember before when we were on this floating point, you did some calculation and you had some computation that ended up being not exactly representable, and we had to say, we're talking about rounding, is it round down, is it round up? What happens? Well, when it would have been in the middle, he stores the bit to say, you know what, we did some rounding, it wasn't exact, and this U-bit tells you whether the number in my calculation was exact or not. So if it actually can end up, 2 to the something, that's certainly representable perfectly, because 2 to the something we can do really well if it's in our range. And what if I double that? Well, that's also in the range, because we can do powers of 2 really easily. Well, then that would say the U-bit is off, because I'm exactly snapped to a value. But if ever the calculation was in the middle, then I'm going to eventually have to snap to a value of a U-bit, whatever the Unum is, the closest Unum, they call them Unums, the closest Unum is, I'll snap to it, and I'll set the U-bit to 1, saying, you know what, I had to do some rounding. So it's like, remembers whether you did rounding or not, or whether you had to. If you didn't have to, U-bit is off. If I had to, U-bit is on. That's very clever. So this quote, this boastful quote, I'll say, I'll even go on record saying that, said, it promises to be to floating point what floating point was to fixed point, which is kind of true in a way. You think about, we locked in where the binary point was. Let's make it more general with this knob over here telling you where that point should float. And he's adding another knob that says how many bits in each of the exponent or significand I'm going to give. And so that is actually a bit more interesting. If I needed a lot of precision, then give a lot more bits to the significand. If I need a lot more range, give a lot more bits to the exponent. That makes sense? So it's very clever to think about how you do this to be able to have even more range. So Unum hasn't been formally adopted by every piece of hardware, but it's getting more adoption. I think it's actually a very clever solution. So claims to save power as well. I don't know whether I can support that claim, but that's another claim they have. In summary, last slide. Floating point lets us represent numbers containing integer and floating point parts. We can do big numbers, we can do small numbers. Amazing. IEEE 754 floating point standard earned one of my colleagues a Turing Award, the Nobel Prize in Computing, for that work. Every computer since 1997 before then was having a different way it did it. HP was different from Apple, which is different from Intel. It was crazy, it was chaos. This floating point standard standardized everybody, and now we're all using this floating point standard. By the way, that has revisions. There are revisions to this where they try to correct some things and add things. There's always a revision to that. You saw the revisions to C. There's revisions to the IEEE floating point standard as well. They usually say IEEE 754 underscore the year, which is kind of nice. In 4 digits, not C99 with 2 digits, just have 4 digits for that, so it'll say underscore 2008 or something like that. And I think there's a 2019 out there recently as well. So summary, this is it. You've seen examples. You've seen pictures, you've seen ways you can play with an interactive, touch the bits and play with it and explore that. I encourage you strongly to do that. S, exponent, significant, everything follows this format. Every other format basically is just changing the widths of the exponent and significand to do different things. But FP32 is the default. When you say float, that's what you get. Remember, exponent is telling the significand how much, what power 2 to count by. Are you counting by quarters, or halves, or ones, or twos? So you're always counting by power, or minus 149s. That's what's the smallest one. So the exponent tells how much to count by, then the significand is just counting by that much. That says how wide are the ruler values. So the exponent says, tell me how wide my ruler lines are, and then the significand counts by those ruler lines. It's always an equal. So it's and then bup, 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 and then bup, 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 like that, if you kind of did the sound. And there's this benefit that you can store nans, you can store plus or minus infinity, you can store debugging information in your nans. We love all this. I'm going to take you out with one of the greatest 70s soul R&B songs. It's called Float On by the Floaters. Just boogie along to me. Float on. I'll just dance. We'll see the next module. Take care.